This is our first lecture, and we're going to be discussing classical methods of measurement. So there's three basic methods we're going to be talking about: the method of limits, the method of adjustment, and the method of constant stimuli. And then we'll talk about some biases that may come into play with those methods. So some facts about the classical methods. The classical methods are not really as reliable as modern adaptive methods. They don't eliminate bias because we don't really know where the subject's criterion is. So what are they using to say, yes, I heard that, or no, I didn't, or yes, that matches, or no, it doesn't? We're not quite sure what the subject is using. Also, it's difficult to separate bias and sensitivity. So what are they using as their response bias, and then what is their true sensitivity to? So all of these things come into play as we're examining these different methods for establishing threshold. So there's two behaviors that are of interest when we're talking about classical methods. There's detection and discrimination. So some of the methods you can use detection. Is the sound there or is it not? Or discrimination. Is this one louder than the other? Is this one higher in pitch than the other? Something like that. So the three methods, like I said, that we're going to discuss are the method of limits, the method of adjustment, and the method of constant stimuli. So the first one is the method of limits. And the method of limits is similar to the threshold measurement that you're probably used to using in the clinic. The experimenter controls the stimulus just like the clinician controls the stimulus in the clinic. And the levels are changed in discrete steps. So we do that as well in the clinic. With the method of limits, we can use an ascending or descending, or actually both, one sweep ascending and one sweep descending, or vice versa. And what happens with the method of limits is the subject then is going to make a judgment after each presentation. So they're going to say, yes, I heard that, or no, I didn't hear it. And some of the biases that are involved with this method, the first one is anticipation. They're waiting to hear that sound, and they may actually respond too quickly. Usually the bias is better with ascending and poorer or having more of effect with descending. So thresholds will be better when you're using the ascending method, so the sounds are getting louder as you go, as opposed to a descending threshold where they're getting softer as you go. Habituation is where they get used to responding one way or the other, and you'll have poorer ascending thresholds and better descending thresholds. So here's an example of a method of limits in an experiment. We have the stimuli along the column on the left, and that's in decibels. So it's softer at the bottom and louder at the top. And then we have the runs across the x-axis at the top. And then you can see positive means that they said they heard it, and a minus means they said that they didn't. So it looks like we're going roughly 2 dB steps. And so at 34, they heard it in run 1. At 32 dB, they heard it. At 30 dB, they heard it. 28, 26, 24, 22, on down. To 14, they heard it. And then 12, they didn't. So the threshold is considered to be at 13 dB. So then the next one is an ascending run. And at 4, they didn't. 6, they didn't. 8, they didn't. 10, they didn't. 12, they didn't. 14, they didn't. 16, they didn't. And then at 18, they did. So the threshold is considered to be at 17 dB. So you get the idea, going all the way across. And there were 8 runs. And after the 8 runs, then all of those 8 thresholds are averaged together, and the mean threshold is considered to be 16 dB. So to minimize biases in the method of limits, use equal numbers of ascending and descending runs. So in the previous example, you had one and then the other and then one and the other, but you had equal numbers of ascending and descending runs, and you stop between runs to give them a little bit of a rest. You don't tell the subject which type of run is being presented. I mean, after a few presentations, they can usually figure it out, but you're not going to tell them to begin with. And you're going to vary the starting levels of the run, so you don't always start at the same level. And you can see that in this previous presentation. If you just look at the descending runs, the first one started at 34 dB, and then run number 3 is the next descending run, and it started at 30 dB. And then the next descending run is run number 5, and they started at 28 dB. And then the next descending run was number 7, and they started at 34 dB. So that's another way to reduce bias. And another way is to present a different number of stimuli within each run. And again, you can see that on the previous slide as well. Looks like the run with the most presentations was probably run 1. I mean, I'm just guessing here, but it looks like it. But you can see there's a different number in each one. The yes-no presentation is very common. And if we think about it, the probability is 1, meaning that there's always a signal present. The subject will always assume that a signal is present when they have to say either yes or no that they heard it. So the person knows that the signal will be there even if they can't hear it. Now the next method is the method of adjustment. And in this case, the subject controls the stimulus rather than the experimenter controlling the stimulus. And there'll be a control knob that they use to adjust the stimulus, but it's not labeled or marked in any way. And it's continuously variable, so there's no discrete steps, so they won't feel a click or anything like that when they turn the knob. The experimenter controls where the stimulus starts, and again, we have ascending and descending runs. And what happens is we're establishing an absolute sensitivity. The level is adjusted until it's either audible or inaudible. And a differential sensitivity, which is you're going to adjust the level of one signal until it's as loud as a standard. So there's 2 different ways we can do this. With the absolute sensitivity, the subject is adjusting it until either they hear it or they don't hear it. Or a differential sensitivity, they are using a comparison signal or standard signal, and they're adjusting the level of one until it's as loud as the other, or you could even do it as the same pitch as the other, depending on whether you're doing a loudness or a pitch study. So the biases here are persistence or preservation. And with that, you're going to have a better descending threshold and a poorer ascending threshold. And to minimize bias, you're going to use ascending and descending series equally again. And you can have the subject bracket their threshold, so hone in on their threshold rather than just one time adjusting to whether it's audible or inaudible. They can go, inaudible back to audible and then back to inaudible again. And then you're decreasing the step sizes as you go to bracket down in onto that threshold. An example of this is a Bekesi tracing. Now I'm dating myself, but back when I first started practicing audiology, we actually used Bekesi audiometers. And a Bekesi audiometer uses an adaptive procedure, which is a type of method of adjustment. And what happens is the signal will actually change at a fixed rate that's set by the experimenter. But the direction of change is controlled by the subject. So what happens is, say you're going for a threshold, loudness threshold, and so the participant has a button, and they're going to push the button and keep the button down for as long as they hear it, and then the level keeps decreasing while they keep holding that button down. And as soon as they don't hear it anymore, they let go of that button, and then the level is going to increase in loudness again until they hear it. And then they're going to push that button again and hold it down for as long as they hear it again. And as they're doing this, frequency is also sweeping as well. So you've got a loudness adjustment going as well as a frequency sweep. The advantage to the Bekasi tracing is that their speed and precision. The bias is subject reaction time, especially older listeners or younger listeners may not release or press that button as quickly as they could, and obviously variations in what they're using as their criteria to respond. So here's an example of a Bekasi tracing, and you can see that time is going across that x-axis, and then we have the stimulus level in dB, and you can see audible is above the dotted line, which is the 50% point, and inaudible is below that dotted line. Then there's the method of constant stimuli. And with the method of constant stimuli, you're going to present various stimulus levels in random order. So it's like the method of limits, but it's non-sequential. So there's no ascending or descending runs. You're just presenting, you've figured out how many presentations you need to make, and you're just presenting them in a random fashion. It can also be yes, no. Yes, they hear it. No, they don't. So in this case, the probability of the stimulus being present is not always 1, because there may be some times where you don't present anything. There's an equal number of stimuli presented at each level. And what happens then is you present all of these stimuli, so there's a whole bunch that you have to present, and then you tabulate the results and you plot a psychometric function. And then you can calculate a certain point on the function or the slope of the function itself. So here's an example of a table. You have different stimulus levels, and you have the number of responses and then the percent of responses. So for example, there were 50 presentations at 11 dB, and they got 100% of them. But then you drop down to 9 dB, they only got 47%, so that, 47, so that's 94%, and so forth. So then what you can do is plot a psychometric function. So again, you have these stimulus levels. Remember they're right here, 4, 5, 6, 7, 8, 9, 10, 11. So they're along that x-axis now. And you've plotted then how many responses, or the percent correct responses on your graph. So example, at 4, they had 0, so it's plotted at 0. And then let's go up to 8 is, if you go to 8 across over to your right, it's at 70%, so that's plotted at 70, and so forth. And then you have your psychometric function. So then you can find the 50% point to tell you that the threshold corresponds to 7.5 dB. And so here you are again, A, which is the top square up there, is the psychometric function. It's a different one, but same idea as to what we just looked at, where the threshold is at 17 dB. B is the responses obtained at 0%. We're at 14 dB, and 100% we're at 24 dB with a 10 dB step size. And then C shows you there's percent responses at various levels with a 2 dB step size, and the 50% threshold is shown on each graph, so you can see it there. So here is data from an experiment on differential sensitivity for intensity using the method of constant stimuli. So you have 2 tones, and they're comparing 2 tones for intensity. And this is the level of the second tone. and then on the left-hand side, and on the right-hand side is the percentage of louder judgments. And so here is the psychometric function of the results, and you can see the psychometric function for differential sensitivity showing the point of subjective equality, or the higher threshold, and the difference Lyman. And this is all from table 7.2, which is this table right here. So again, you can find that 50% point, which is the point of subjective equality, or PSE, or you can do a difference Lyman there showing what was the point where they actually could hear a difference. What happens with the difference Lyman is there's a certain point where things will change and the person doesn't hear a difference. Things will change and the person doesn't hear a difference. Things will change and the person doesn't hear a difference. And then all of a sudden they do hear a difference. And that's going to be the difference Lyman. So with the method of constant stimuli, you get the whole psychometric function, but a lot of times you're only interested in that 50% point, which we use as threshold in the clinic. Sometimes in studies you might want to use the 80% point, just depending on what you're looking at. But usually clinically we're looking at a 50% point. The advantages with the method of constant stimuli is that you can include those catch trials to help reflect bias. Remember, so then the probability isn't always 1 that there's a stimulus there. It is more accurate, but as you can tell, you have to present a whole lot more trials for this type of method, and you also have to calculate the percentage correct, and you have to plot the psychometric function and all of that. So it's less efficient, but it is more accurate. So if we convert this, if we look at modern adaptive procedures, with modern adaptive procedures, we look at the level at which the stimulus is presented, and it depends upon the subject's response to the previous stimulus. So that's why it's adaptive, because it's changing depending on how the person responded. You can then converge on threshold and place most of the observations around it. So with adaptive procedures, you try to control for bias and focus on the measurement itself. You're going to maximize precision and efficiency so you don't waste any trials at the ends of the psychometric functions. If you think back, there was like a tail at 100% and a tail at 0%. And so you're not wasting trials at those tails, basically. And you set up rules for accepting and rejecting data beforehand so that it makes it more efficient. So there was a study by Levitt in 1971, and he used a simple up-down or staircase method. He used a single interval yes-no procedure, and it was different from the method of limits because the testing didn't stop on the reversal. Remember back when we were talking about the method of limits, we stopped as soon as they said yes, they heard it on an ascending, or no, they didn't hear it on a descending. So this was a little bit different. And threshold was the average of 6 to 8 reversals. It was similar to the method of limits because there were discrete steps that were used. And with this type of threshold estimation, you can add catch trials and you can change the step sizes if you want. And with this method, you can converge on the 50% correct point. So you can use a transformed up-down method, and the rules for changing the stimulus are set up beforehand as to how you're going to change the stimulus following each response, meaning how are you going to change that stimulus, step size, if they heard it or if they didn't hear it. So here is figure 7.7, and it's showing the first 6 runs of a threshold search using this simple up, down, or staircase method. Each plus indicates a positive response, meaning they heard it, and each negative indicates a negative response, meaning they didn't hear it. Odd numbers are descending runs, and even numbers are ascending runs. The first reversal is generally omitted from the threshold calculation just because the participant is getting used to the process. So in this case, the stimulus started at 16 dB. The person heard it. It went down to 14 dB and they heard it. 12 dB they heard it. 10 dB they heard it. 8 dB they heard it. 6 dB they didn't hear it. So it reversed and it went up to 8 dB. They didn't hear it. It went up to 10 dB and they did hear it, so it started descending again. So you get the idea going across. And like I said, when they are calculating threshold, they're going to throw out that first run. So that first descending run is going to be removed from the threshold calculation. So here's an example of the transformed up-down procedure and how it converts on the 70.7% correct point, which is used a lot in psychometric threshold estimations, such as in gap detection. The 70.7% correct point is used a lot. And then at the other end of the spectrum, the 29.3% correct point is also used. So you can see again how it's they didn't hear it, they didn't hear it, they didn't hear it. There were 2 trials. They did hear it, but then they didn't. They did hear it, but then they didn't. They did hear it, but then they didn't. They did hear it, but they didn't. And then we reached a spot where they heard it at both trials. So then it reversed direction. They heard it at both trials, so it went down again. They heard one but didn't hear the other one, so it went back up. And you can see how these, how it's converging then on a threshold. So here you go are the groupings. Entry 1 was a negative, and if they didn't hear it, then the level is going to increase. And for a down group, if they did hear it, then you're going to decrease the level. And then here's the math showing the probability of a sequence from a down group or a positive response at conversions. So you can see the different probabilities there. And again, the 70.7, which is number 2, is the one that tends to be used a lot in psychometric measurements. So you can see also how the number of trials that are used for each step size, whether it's 1 time yes or no, 2 times, 2 trials at each level, or 3 trials at each level, or like number 5, it's 4 trials at each level, how that affects that probability percentage. So 2 times at each level, you're at the 70.7, whereas 4 times at each level, you're at the 84.1, just to point that out. So there's another study by Taylor and Creelman in 1967, and they looked at fixed versus adaptive procedures, and basically you're trading serendipity for efficiency. So you're trying to get more efficient with the measurements, and they looked at PEST, which is parameter estimation by sequential testing. And what that does is it uses the changes in the direction and step size to hone in on your target. And you set the target to any location on the psychometric function. So do you want to be at the 50% point? Do you want to be at the 70.7% correct point? Wherever it is you want to be. And the goal basically is to have a minimum number of trials wasted, because you want to be efficient and use as little number of trials as you can, both so that your participant doesn't get tired and also just for your testing time in general. So here's an example how the threshold was attained with the PEST procedure. The points are identified by letters. They're discussed in the text, and actually that paper, in fact, all of the papers that I'm discussing are in your interactive module, so they are available for you. So you can see there they're showing the 2 dB step size, and you can see how some of the steps were larger than others. So it just depended on where they were. At the beginning, the step sizes were larger, and then as you started to hone in on the threshold, looking at F, G, H, and I, you can see how the step sizes got smaller to hone in on that threshold. So in other words, you're using big step sizes at the beginning, taking big steps, just trying to get the ballpark idea of where the threshold is, and then you can hone in with smaller step sizes. So a series of rules for doubling and halving the stimulus level depending on the previous sequence of responses, like I just talked about. And then you can divide them into groups, with each group will explain. Oh, sorry, just ignore that. That was for a previous lecture. So don't worry about that. We're not going to divide into groups. So don't worry about that. Okay, popular procedures then are the transformed up-down procedure. You have to have an up rule and a down rule. And again, that Levitt paper is available for you to read. Forced choice procedures, where the subject listens to 2 or more stimuli and must choose one based on a certain parameter. You can use a 2 alternative forced choice, meaning they're given 2 choices and they have to choose one or the other, or a 3 alternative forced choice, meaning they're given 3, like usually one will be a standard and then there'll be 2 others and they have to choose one or the other, and that's a very popular way to establish threshold. Now don't confuse the number of alternatives, the 2 alternative forced choice or the 3 alternative forced choice, with the number of up or down rule. Those are 2 very different things. Right now we're talking about how many they're presented with 2 sounds or 3 sounds and they have to choose one or the other. That's different than how many step sizes we're using. Okay? And then adaptive measures will often result in lower thresholds than non-adaptive measures, just because they're more efficient and they get to the threshold more quickly. The participant or subject doesn't get tired as often or as quickly, and they don't require as many trials. So Campbell and Lasky has a paper, have a paper that was published in 1968. Again, that's in your interactive module, and they used a block up-down temporal interval forced choice. And what this does is it replaces the single trial per stimulus level with a block of several trials per level. And you change the level after 3 or 4 correct responses for 75% correct, or for 5 responses for 80% correct. And you can use the yes, no, or you can use a 2 alternative forced choice procedure. And you can change the number of trials in the block and the rule to target the percent correct, just like on line 3 there. And you also can determine the false alarm rate as well. So you can determine how many times they're responding when there's nothing there, or they're giving you responses that they did hear something when there wasn't anything. So you can establish all of that with this block up-down temporal interval forced choice. So here's an example. of a convergence on the 75% point of the psychometric function using a blocked method. So you can see they're presenting 4 presentations at each level, and the pluses mean that the person said they heard it, and the negatives mean that the person said they didn't. So they're honing in on that 75% point using this method. So 75% obviously with 4 would be 3 out of 4 were heard. So in clinical audiology, there are several different methods that are used that are very similar to these psychometric methods, and I'm sure you're familiar with them, the Huson-Westlake method and the Carhart and Jerger method, where again you're using ascending and descending methods, and you're changing whether you're ascending or descending depending on whether the person heard the tone or did not hear the tone. That's what we do clinically. We're going down in down 10, 5 up. So you're going down in 10 dB steps. When they hear the sound, you're moving quickly, trying to get down to a soft level quickly and efficiently. But then you're going in smaller steps as you go ascend, because again, you're trying to hone in on that threshold. So it's like the method of limits, but you use the ascending trials to search for threshold and the descending trials just to reposition. And again, the Bekesi tracing, like we talked about before, there's another picture of that in your interactive module as well. And then there was a study by Leek, which again is in your interactive module in 2001. And he looked at the PEST again, and he was looking at maximum likelihood. So the stimulus presentation is dictated by the current best estimate of underlying psychometric function after every response. And a new psychometric function is generated after each set of trials. And you may have to establish the psychometric function through a series of studies first. Then there's the staircase method, which again is in that Levitt slide, which is simple by comparison. You're using the previous response to select the next stimulus and the average reversals for threshold or the just noticeable difference. So there are some problems and considerations as we talk about these different methods. Learning. When does performance stabilize? When does the subject learn what we want them to do? When do they fatigue? And of course, both of those things are going to vary from person to person. And of course, the age of your participant as well. Very young and very old listeners are going to fatigue quicker. And again, changes in attention. They may be paying close attention at the beginning, and then as the testing goes on, the attention may wane. So all of these factors and considerations play a part just about any time we're establishing threshold. There's a learning curve at the beginning, and then we have to worry about fatigue and changes in attention that occur as testing time goes on. So we want to try to use the most efficient method that we can that will establish a reliable threshold quickly and with as few trials as we need to use.